welcome to my presentation on BIM-based variant retrieval of building design using case-based reasoning and pattern matching. So first I would like to describe the main motivation. This is the support for the architects. The proposal I'm going to show should inspire the architects in early design phases with different variants of building designs to calculate, for example, early effects of the building and avoid mistakes. Therefore, it is important to find a way to provide the implicit knowledge of individual planners and architects as explicit knowledge for everyone. The compatibility with BIM models is very important because it's orientated to the everyday life of a planner or architect. So the paper shows a way to identify suitable building designs for an existing project and how to change variants. Yes, this is a fast identification of suitable building designs from different points of view so that you avoid mistakes, for example, or can analyze some buildings in early design phases. What research approaches exist? Yeah, in the recent past, you can find different approaches of graph modeling in construction projects. 1996, there was a basic idea of finding suitable design options for floor plans, but without connection to BIM. Concerning this variance, I would like to relate to my paper. The CBR approach was proven useful in the later past in combination to exact or inexact pattern matching, and I will start with that in the next slides. Early in this research, a way to save the IFC structure of a BIM model as a graph was developed to be able to compare it later on, and structure, function, and product variants were identified and implemented. Therefore, I would like you to relate to the paper. For those who have no experience with the topic, I have included an image of a building as a graph on the right side so that you can imagine how a floor plan, for example, can look like with the edges and the nodes. Maybe some of you know the CBR process. It's the case-based reasoning, but let me shorten it up. It is a way of problem finding using problems that have already been solved and proven to be successful. Buildings are mostly heterogeneous, so it is more difficult than in other disciplines or applications. And in this paper, we focus on the retrieve process of the CBR so that we find a solution to a problem and match it with some database entries. Next to a matching method, it is necessary for the CBR to determine a degree of similarity. And this paper is dealing with this retrieve process and with the possible solution for this process. The used matching method is in the paper the graph pattern matching because of the representation of the IFC data as a graph structure. There is a difference between exact and inexact graph pattern matching. Exact means you have the same number of nodes and the same connection with edges, so some kind of an isomorph graph. And inexact matching means that there can be a difference between the number of nodes and edges, so it is more heterogeneous and more suitable to the building. To get an impression, in figure 5, you can see an inexact pattern matching. The pattern on the left is searched in the database, and the pattern on the right is the kind of inexact pattern match. So it is nearly the same, but you could have another connections or another options. This is another simple example what graph pattern matching could look like. First, the pattern have to be defined with rules. On the left side, you can see some kind of search parameters for the same door, for example, in other graphs. Door is an opening element and connects to two sides, and maybe a bedroom with a bathroom. And in the second step, all stored graphs in the database are searched for those structure, and in addition, maybe with other options stored in the graphs. However, the search depends on the similarity so that you can define a graph that is a subgraph of a database entry. Why do I have to determine a degree of similarity? If someone wants to compare two graphs, he or she won't find a one-to-one isomorphism because no existing problem is completely like a solved problem. The weights we use in the paper help the user to get better results concerning his requirements and describe the importance of the features. The given similarity calculation is implemented in the pattern matches so that the graph database is searched for graphs which comply with the permitted deviations. Most entities in the BIM model have quantities and properties. In the paper, we define deviations for both of them. Some deviations are simple, for example, Boolean in case for some properties of a door. Others are more complicated, for example, the differences in the volume or in the floor area. And the outcoming similarity score tells the user how similar the outcoming variant is to an existing problem. So you have, for example, the IFC building story as entity with the gross floor area and the gross volume as quantities. And the user then weights how important the IFC building story or the gross floor area is for him. And then we take a look at the deviation and normalize this factor for the calculation of the similarity. Let me quickly summarize the whole process we address in this paper. In a database, for example, the decay space, some variant graphs are defined as graphs which contain option points. These variant graphs are documented by previous users with a defined structure, function, and product variants. A new user, for example, an architect or a planner, specifies a problem with different parameters for the upcoming project. For example, the use of the building story, the sizes, the number of function of the rooms. And he or she is able to set connections if these are important for him. This could be a connection of two rooms, for example, a bathroom with a living room. And afterwards, the user has to weight specific parameters, how important they are for him, so that therefore the similarity calculation could retrieve some possible variants. And the specific search parameters are compared with the variant graphs stored in the database, and the matching results are returned to the user. At the end of the process, fine-tuning can be done, which will show possible further structure, function, or product variants for a selected area without affecting the structure of the building. For example, to change a door or to change a window or to change a load-bearing wall into a non-load-bearing wall with some effects of columns or something like this. This shows a visualization of the described problem by the user and the outcome simplified graph structure. This graph structure is searched in the database. For example, on the left side, there is the problem definition, the visualization of the problem definition, and on the right side, there is a simplified visualization of the problem as a graph. The graphs have always the same structure, so there's always the IFC site, the IFC building, one or two IFC buildings, then the IFC building stories, and there come the walls and the windows and spaces. One result can be the graph on the right. The colorized edges and nodes represent variance that fits into the user's idea of similarity. These results are a possible solution because the graph of the described problem is a subgraph of the graph on the right. And in case of the similarity deviation, this is the outcome. So the outcome of this process is the most similar solution of the database entries. In that case, the similarity score was calculated to 0.86. And the similarity score is always between 0 and 1. 0 means no similarity and 1 means full similarity. On the left side, for example, you can see the function, structure, and product variants, which changes to the problem. And yeah, they are also visualized. The paper shows a concept for a BIM-based retrieve process to find similar building designs and possible variants. In ongoing research, the similarity calculation needs to be improved to get more specific results. For the CBR process, it is important to have a big database, and therefore it is necessary to find a method in which machine learning can fill these databases. For the, investigate pattern matching and compare it with alternatives is also an ongoing process, and we would like to develop a user-friendly interface that don't get too complicated with the weightings of each entity. And in the end, we want to do